So welcome back, students. We'll continue our discussion on the binding energy of a nucleus or an atom. We said when the nucleons come together to form the nucleus, when you say nucleons, the term includes both protons and neutrons. When they come together to form the nucleus of an atom, part of the mass is lost and that gets converted into energy, and this is what you call as the binding energy of the nucleus or the atom, the binding energy of the nucleus. So the nucleons, meaning protons and neutrons, they come together. When they come together to form a nucleus, they lose a part of their mass, and the lost mass gets released as energy, and this is what we call as binding energy. I want you to understand that. This is the binding energy of the nucleus. So the bigger the nucleus, you can expect greater the released energies. So the binding energy will be more for bigger nuclei, because each of the nucleons will lose a certain amount of mass, and in a big nucleus we'll have a lot of nucleons, and each of them will lose a certain amount of mass. So the energy that you get out when they are formed is going to be big. A lot of energy is what you're going to get. It's a lot more energy than you would get from a lighter nucleus. So this is what is called as the binding energy of the nucleus. Binding energy of the nucleus. The nucleus. Okay. So the nucleons come together. Nucleons, meaning protons and neutrons, they come together to form the nucleus. So like this, they come together. So when they come together to form the nucleus, you see a certain part of the mass would be lost. Okay? So this part of the mass will be lost, and so when they come together, then energy is released. So the bigger the nucleus, the greater the energy you can expect. So the binding energy, the energy that is released when the nucleus is bound. Okay? So that is the binding energy is called as B. This is greater for bigger nuclei and smaller for smaller nuclei. Understand? So there are only two which combine to release the energy. Like let's take deuterium. If you take deuterium, then there is one proton and one neutron. They come together, so they combine. So part of the mass would be released. So only so much mass is lost. The mass defect is small here, so you get a certain amount of energy for that nucleus. Then when you have helium, for example, there are 4 of them, right? So that you have 2 protons and then 2 neutrons. So when they come together, it could be something like this, right? So you see, each of them would be losing a certain amount of mass. Now you have 4 nucleons losing energy, so you have greater energy coming out of this. This could be deuterium and this could be helium. Greater energy. So the binding energy for deuterium will be smaller than the binding energy for helium. But what about the binding energy per nucleon? Each of the constituent parts, each proton, each neutron is going to lose some of its mass, right, when they come together. So, what is the contribution of each nucleon, meaning either proton or neutron, in this process? See, that can remain constant. It's like this. Okay. What I'm saying is, you have two classes. So you have, in one class you have say 50 students, and in another class you have 100 students. Suppose each student contributes 10 rupees for some cost. So the first class, where you have 50 students, will give you 500 rupees because you have collected 10 rupees from each of the students. So 500 rupees is what you get from the first class, and then the second class will give you 1000 rupees because there are 100 students in that class. So the amount of money that is coming out of the first class is 500, and then the amount of money that is coming out of the second class is 1000. So clearly, the bigger the class, the greater the money that you get. But you see, in each class, each person contributes just 10 rupees. So likewise, you have two nuclei. The bigger nucleus will give you greater energy. The smaller nucleus will give you less energy. But is it possible for the nuclei, each nucleon in these two nuclei, to contribute the same amount of energy? Is it something like this? Is every nucleon is contributing 10 rupees? That is what we are going to find out now. See, even if you take these two classes that we talked about, one class having 50 students and the other class having 100 students, let's say the 50 student class contributes 10 rupees per head, so 500 rupees. I said this class where you have 100 students also contributes 10 rupees, so then you have 1000 rupees. 500 is less than 1000. 1000 is greater than 500. But let us suppose the second class contributes only 8 rupees, not 10 rupees per head. Only 8 rupees per head. So there are 100 students there, then you are going to get 800 rupees. This 800 is still greater than this 500. So the bigger the nucleus, you still get greater energy. Okay. 800 is greater than 500. But then you see the contribution per head is different here. The contribution per head in the first class is 10 rupees. But the contribution per head in the second class is 8 rupees. So the binding energy per nucleus, even though it's a good measure, isn't really talking about the individual contribution from the nucleons, from either the proton or the neutron. It doesn't give you a good figure of that, a good understanding of what's happening in a bigger nucleus. So apart from this binding energy, which is anyways going to be greater for a bigger nucleus and the most part, bigger nucleus and smaller for a smaller nucleus, we need one more quantity which is called as binding energy per nucleon. Okay? So binding energy per nucleon, I call this as Bn. This is binding energy, Be, binding energy per nucleon. This is B, this is Bn. And how do you calculate it? Well, you take the nucleus, you find the binding energy for the nucleus, and then if you average it out, if you divide it by the number of nucleons in the nucleus, then you are going to get binding energy per nucleon. Okay, so binding energy per nucleon Bn is equal to binding energy for the nucleus B divided by A, which is the mass number. So this is binding energy per nucleon. Okay. So this binding energy per of the nucleus is called as B, and B is greater for bigger nucleus and smaller for smaller nucleus. And then you have one more quantity which is binding energy per nucleon. Okay, because the nucleons are both protons and neutrons. So you call proton also as a nucleon, and neutron obviously. Like anything which is in the nucleus would be called as the nucleon. So protons are the nucleus, so protons are nucleons, and neutrons are also nucleons. Okay. So this is an important idea. So this binding energy of the nucleus is one thing. It's like 500 rupees per from the class, or 1000 rupees or 800 rupees from this class, the other class. So that's a binding energy of the nucleus. Then binding energy per nucleon is the contribution per head. Okay, so that's a very important thing. So in our example, if we were to say class A, let's say this is class, we will draw a graph. Okay, I took class A. Okay, so I'll say class 50. Class 50 students are there in the class. So 10 rupees was a contribution from each head, so it gave you 500 rupees totally. Then class 1000, class 100, class 100, again 10 rupees, when it contributed 10 rupees, then you get 1000 rupees. So even though these two numbers are different, these two numbers are the same. So if we were to draw a graph, this is the binding energy or the contribution per nucleon, and then this is a class, this is class 50, and then this is class 100. Okay? This is a class. And you see both of them contribute the same amount. This 10 rupees and this is also 10 rupees in this case. Okay. If you draw this, then you see the contribution is the same from both classes per head. But then the amount of energy that is coming out of this will be greater. This will be greater than this. This will be 1000. This is going to be 500. I want you to understand the difference. This I can draw two graphs basically. I can draw two graphs. One graph could be this. What is a graph? This is binding energy of the nucleus. So if I have class 50, then I'm going to have 500 here, and this is class 50, and if I have class 100, then I'm going to have 1000 here. So this is the binding energy of the nucleus. But when I do binding energy of the nucleon, then you see both of them contribute only 10 here. If the other contributes only 8, then it can actually come down. But even in that case, this will be more than this one. I want you to understand this. So there are two ideas: binding energy per nucleus and binding energy per nucleon. Binding energy per nucleon is the average contribution from each person. Sometimes it may be greater in the case of a smaller class than in the case of a bigger class. We saw that if the 100 people class contributes only 8 rupees, you get 800 rupees. 50 people class contributes only contribute 10 rupees, you get 500 rupees. So you got only 500 rupees, but then you got 800 rupees. The contribution from the class is more here. The contribution per head is more here. Okay, so they could be different. So these two numbers can be different. Okay, they can give you different pictures. Okay, B could be greater for a nucleus, but Bn could be smaller for it. And for another nucleus, B could be smaller, but Bn could be greater. Or for another pair, Bn could be the same. Okay, each can contribute 10 rupees or so. So all this type of combinations are possible. So binding energy per nucleus and binding energy per nucleon are two different things. I want you to understand this. So we're going to expand on that idea of binding energy per nucleon. We have lots of elements, and each element has its own isotope or isotopes. As we just saw, gold has about 32 isotopes, so each element will have many isotopes. So the nuclei of all these elements are going to be different. And if we were to plot a graph of the binding energy per nucleon against the atomic mass number, the mass number, if you take the mass number on the x-axis and then if you plot the binding energy per nucleon on the y-axis, then you are going to get a curve. And if you look at the curve, then that curve can give you some insights into what is happening inside the nucleus in general. You will be able to gain some insights about the general nucleus, like how a nucleus will behave by looking at this curve. So that's what we are doing here. Okay? You can see this curve. You have the mass number on the x-axis, and then this is binding energy per nucleon. It is not the binding energy. Okay? I want you to focus on this. This is binding energy per nucleon. I told you, the bigger the nucleus, you will get the bigger the nucleus, the bigger the binding energy will be. But we are not talking about binding energy per nucleus. We are plotting it against binding energy per nucleon. So it's the average energy nucleon. So that's what we are plotting. Okay, so like if you have the 50 student class and then 100 student class, then if both contribute 10, then irrespective of the mass number, you should have the same point here. So 10, 10. That is, so that's the idea here. So it doesn't depend on the number of people in the class, but how much they contribute per head. So the per head contribution is what we're plotting here. So you have mass number, and then you have the binding energy per nucleon, the per head contribution of the nucleon. Okay. So when you do this, you get a curve like this. You can see that, this is H2, and then this is H3, this is H2, is mass number. Which one will have H2? It's going to be deuterium, and this would be tritium, H3. Clearly, what's the binding energy of hydrogen? 0. Because there is nothing to bind. There is only one proton. What would it bind with? It's nothing. So there is no binding energy for hydrogen. But there is binding energy for deuterium. Hydrogen, the isotope of hydrogen. And there will be binding energy for tritium. Because even though they are hydrogen atoms, they are the isotopes of hydrogen. So the nucleus now it doesn't have only one proton. It has one proton and one neutron or two neutrons. So you need to bind them now. So this would be the binding energy for deuterium. This is tritium. You got helium here, and then lithium comes down. Okay. And then you have sulfur here, iron here, then molybdenum, then iodine here, and tungsten here, and then uranium 238. So that's the mass. It's not the atomic number. It's a mass number. So you're plotting this. So look at this. So this is the graph. So what it says is that when the elements are light, okay, then the binding energy per nucleon is less. It's like this. You have a class of say 10 people, And if you have a class of only 10 people, then each of them contribute only say 5 rupees. Okay? So they contribute less. If you have a class of say 20 people, then they contribute say 7 rupees per head, something like that. Okay. So it is like I do it again. So it's a class. Okay. So there are 10 people in the class, then contribution per head, it's going to be somewhere like it's 5. So the total would be 50. Okay, this is B, that's different. Then if you have a class of 20, then they contribute say 7 rupees or something. Then you get 140. See, more. Now you have a class of 30, is rupees, right? The contribution per head. So it could be say 8 rupees. 240. If they contributed only 5, then it would have been 100, it will be 150. But no. See, the contribution becomes bigger. Notice it? The lighter elements, then the contribution gets bigger per head. It's not the total contribution. Total contribution will anyway be greater. Okay? But it is a contribution per head itself is changing. Okay. Now, let me take a class of say 50. Then the contribution becomes somewhere around 10. Then we get, let's say, start from 40. So now we get 400. Then when it becomes 50, again it is 10. It's not increasing. It was increasing, now it is kind of, reaching its maximum contribution, kind of, per head, saturating. So 10 is going to be 500. And then 60, again 10, we're going to get 600. The individual contribution kind of peaks at this value. Okay. Now 70, then 10, 700. 80, individual contribution is 10, 800. 90, 10, 900. 100, 10, 1000. See, it kind of remains constant at this. Then I have 110, now it becomes kind of 9. Okay. See, okay, or 9.5. So this gives you 990. That's a possibility. Okay, or it can even be 980 or 9.8 or something. Okay? We have 9.5 is what I'm going to get. So this can be around 95. So 1045, right? 1045. Okay. So, the binding energy wise, the energy could be more. But then you see the individual contribution is now coming down. Yeah. Same thing. For example, if you have 120, then it can be 9.3 or something. In that case, what do you get? So it will be somewhere around 1086 or something. Okay, so you get 1086. So it is increasing, but you see, but the individual contribution is going down still. Okay, so if the class is small, then the contribution was small. When the class reaches a certain critical value, and then the contribution becomes kind of constant from then on, then it doesn't depend on the class strength. Everybody is contributing this. And finally, like when the class strength grows more than an amount, then the contribution per head comes down again. So this is how it is. Okay? I am explaining this idea with the classroom and then the contribution in terms of money. So imagine a situation like this. And that is exactly what is happening here. Okay? Notice that the smaller, the lighter the nucleus, the individual contribution. So this graph is this BN graph, right? So the individual contribution is smaller here. But then you see, you reach a certain value here. And from that value, for a very long, from that value, like maybe here it's 30. Okay? About 30 you reach that. From 30 to roughly 170, 30 to 170, this kind of remains constant, roughly constant. It's not much of a variation here, right? And then beyond 170, then it drops. The contribution per head drops. Something similar. Okay, this is rupee per head, and then it's total rupee that is coming out of the class. You see, the total rupee that is coming out of the class is still greater. Doesn't matter. Okay, it's still greater. But an individual contribution is smaller, and then it reached a certain peak value, and then it is coming down again. It's something similar is happening here. Okay, so I want you to understand this. I want you to compare the class contribution with this graph, the binding energy per nucleon. Okay? Now we'll ignore the class. Once you understand this comparison, let's ignore the class and we'll focus on the nuclei. So coming back to the graph, this is how the graph looks like, and over the y-axis you got Bn, the binding energy per nucleon, which is expressed in mega electron volt, and along the x-axis you got the mass number, not the atomic number, it's a mass number. So like hydrogen will figure in two places, yeah, deuterium and tritium. So likewise gold will figure in 32 places, okay, because there's 32 isotopes, right? So along the x-axis. So I want you to understand that. Okay. Now if you look at this graph, this binding energy per nucleon peaks here at Fe. It is 8.75 mega electron volt. Okay. So iron 56 has the greatest binding energy. And then when you come here, uranium 238, it is going to be 7.6 mega electron volt per nucleon. So each nucleon in uranium 238 contributes 7.6 mega electron volt of energy, and each nucleon in iron contributes 8.75 mega electron volt of energy. You can clearly see, even though this contribution per head is more, this would be the amount of energy which is the binding energy for the iron nucleus is going to be less than the amount of energy for the uranium 238 nucleus. Because even though the individual contribution is slightly less than that, you have lots of nucleons. You have 238 nucleons contributing the 7.6 mega electron volt per head. Here you have only 56 contributing 8.7 mega electron volt per head. So the binding energy per nucleus, the binding energy of the nucleus would still be less here, but per nucleon is greater here. Okay, so this is how it looks like. So what does this graph tell you? Let's see, that's a good question. What does it tell you about what happens in a nucleus? Okay. What are the inferences you can draw from this? How these nucleons behave? Okay. One thing is for sure, that is, there is a nuclear force. Because without the nuclear force, we cannot have a nucleus. I told you, if there are only there is no nuclear force, the protons, the electrostatic repulsion among the protons will not hold the nucleus together. The nucleus is there, is present, despite this force of repulsion, the electrostatic force of repulsion, because there is a nuclear force. So that's the first inference. We drew this inference in the very beginning itself. So there is a presence of nuclear force, and it must be very strong. Okay, it's very strong. If it is not strong, then you wouldn't have this. So that's there. Okay. You can't have a nucleus. That is there. Second, we said the nuclear force exists between nucleons. Okay, so nuclear force exists between nucleons, right? Okay, there can be proton-neutron force of attraction, okay? And there can also be a neutron-neutron force of attraction. Okay, so this will pull n towards that, and that. So these are two types of attraction. So you say the nucleons attract each other. Okay. Let's take this case, for example. Suppose I take two nucleons, okay, maybe one here and then the other. So they attract each other. So then they combine to form the nucleus. We told you that there would be a mass defect. Delta M will get converted into energy. Delta M will go as energy. So you will lose a certain amount of mass when they come together. And there are two. This is the amount of there is a mass defect that will go out as energy. So what happens if there are more? Okay, suppose I have three. Let's say I am going to have this 1, 2, and 3. And notice there is a certain amount of mass that will be lost between these two, and it's a certain amount of mass that is lost between these two. So now we have more, right? Like it's like 2 delta M. That is the amount of energy which is going to come out of this. If there are 4, then how are they going to combine? But notice here, is this combining with this? For example, I have something like this. Okay. So you see, they can combine. In that case, there is a certain amount of mass lost here, between these two, between those two. So again, I can have a structure like this, right? So I'll say that maybe I'll ignore this. Let's not worry about this one. I'll go with this. So if there are 3, then I can say that that's 3 delta M mass energy. So there are 4. Now what are they going to combine? If there are 5, what are they going to combine? Each is going to combine with the other, if you think about it. So you take this is combined with this is combined with this. Take this is combined with this, and this is combined with this. If there are 4, then 1 has to combine with all the 3. And if there is 5, then 1 has to combine with all the other 4. So that has to happen for all the other things. Okay. If this happens, if this is what is going to happen, think about it. When they come together, there's a certain amount of energy that is lost when they come together. It's like this. 1, 2. Now this combination, this energy is lost. Okay, then there is 3rd. Yeah? Then this energy is lost. Now it's doubled. If there is 4th, then that should combine with this, right? The 4th should combine with this, and this. All the 3. So it has to lose a certain amount of mass for this, certain amount of mass for that, and certain amount of mass for this. To combine with each. Right? For 2 to combine, there is certain loss of mass. When 3 to combine, I have to lose, if I'm going to combine with 2 more, then I lose certain amount of energy with this guy and certain amount of energy with this guy, because I'm combining with both. And if I'm combining with 3 people, I lose certain amount of energy with this guy and this guy, and then the third guy. You see, I am losing more and more mass. And the same thing will happen to all the other guys too. If we take this guy, he will lose a certain amount of energy with me, and another certain amount of energy with that guy, and then this guy. So this mass will also get reduced. So as there are more and more people, then if everybody is going to be combined with everybody else, like the electrostatic force you saw, right? Okay, combined with everybody else, then more energy per nucleon will be lost. Understand this properly. When I combine with just one person, there is a certain amount of mass I need to lose. When I combine with one more person, I have to lose this mass and also this mass. So as a nucleon, I am losing more mass. So as a nucleon, I have more binding energy per nucleon. Okay? And if there is one more guy, then I am losing mass with this guy, and then the third guy. So you see, now I am losing 3 parts. So the binding energy per nucleon will be even more in this case. So imagine if I were to combine with 10 people and lose some energy for this guy, and that guy, and that guy, and that guy, all the 10. So you see, I am losing more and more mass as I combine with more and more people. Okay. So that is the reason this graph is increasing here. Okay. Hydrogen 2, it combines with only one neutron. There are only this combines with this and this combines with this. This is H2, right? H2, deuterium. Okay. So this certain amount of mass is lost. But then when H3, then it combines with that guy and then that guy. So part of some mass is lost here, some mass is lost here as energy. So there is more loss per nucleon. So that is why Bn is increasing. So that keeps happening till here. See, till this, that keeps happening. But then, the moment you reach this, this zone from 30 to 170, it doesn't increase. If we increase the number of people, the nucleons, I don't seem to get connected with anybody else. Okay? I get connected with somebody, 3-4 people here, okay, around me. But then you bring the 5th person, but I don't get connected with you. I don't lose mass with them. Because whatever I reached here per nucleon, that seems to remain kind of constant. I don't lose much mass there. So I don't have a different binding energy. Okay? Why should this happen? If we were to combine with everybody else in the neutron, in the nucleus, then I will be losing more and more mass as there are more and more people. And I should be having more and more binding energy per nucleon as the size increases. But then it peaks at certain value, like it reaches a maximum. And beyond which I don't lose mass. So what does it mean? It means that I am able to connect with only a few or not everybody. So whoever I connect with, I lose mass. But what is here? Binding energy per nucleon is constant, almost constant in this zone. Which means that I am connecting with only a certain number of people. How many ever people are put there in this range? What does it tell you? It tells you that the nuclear force of attraction is short range. Why? Think about it. Suppose I am this nucleus. I am this nucleon, okay? Then somebody comes here, then I bind with him. Somebody comes here, then I bind with him. Here, I bind with him. Here, I bind with him. Here, I bind with him. Then you bring one more guy over here, I don't bind with him. He's away from me. So this force, this binding force, the nucleus is a strong force of binding that doesn't exist between this and this. So whoever is near me, I bind. Okay, so you bring one more guy here, my Bn is not going to increase because I'm not going to lose any more mass, right? Because I'm not going to bind with him. Now one more, I'm not going to bind with him. One more, I'm not going to bind with him. So how many ever you add after that, my binding energy, the mass I lose in this bond, is not increasing. Okay? So I reach a peak here. So this can happen only if this force of attraction is short range. If the force of attraction is for longer range, then I should bind with this guy also. And if I bind with this guy, then I must be losing some more mass. If I lose some more mass, then the binding energy per nucleon is going to increase. But that doesn't happen. If the binding energy per nucleon doesn't happen, which means that the nuclear force must be short ranged. It must exist only over a small distance, and beyond that distance it shouldn't be existing. There is no binding between this and that. Okay? So the same thing must happen for this also. If I take this one, this guy, I'll use a different color now. If I take this guy, he will bind with me, bind with this, bind with this, bind with this, bind with this, and bind with this. Okay, and if somebody else is brought here, that guy is not going to bind with that person. So whoever is nearby is binding with that person. So for him also, the binding energy per nucleon, okay, binding energy remains the same. And the same thing will happen to everybody else. Let's take this guy for example. I'll use a different color here. This guy. Okay. He binds with this, binds with this, binds with this, binds with this. Okay. He can bind with one more or two more, but then they are not available. I want you to understand this. Suppose this is my nucleus. Okay, I'll put it. I'll complete this. Okay. This is my nucleus. Let me take a nucleon here on the outer surface, okay, of the nucleus. So there are inner nucleons and there are outer nucleons. Let me take this outer nucleon. This outer nucleon binds with this, binds with this, binds with this, binds with this. If there is one more, we can bind with that also. Two more, he can bind with that also. He can bind with them, but you don't have nucleons here to bind with. So this guy will lose this mass, 1 mass, 2 mass, 3 mass, 4 mass. But this guy will lose 1, 2, 3, 4, 5 mass. This guy loses 5. This guy also will lose 5. And this guy, this guy will lose 5. This guy will lose 5. It will be like that. But look at this guy. This guy will lose only 4. Okay. So he will produce less energy than this guy and this guy. So when you take the average energy that has come out, then the nucleons on the outer surface, they are going to reduce this binding energy per nucleon. Why? Because they can have some more bonds, but you don't have some more nucleons to bind with. You can bind only with the nucleons below you, but not above you. There are no nucleons there beyond this outer surface. Okay? But here, the nucleons inside, they have other nucleons everywhere. So they can bind with all the near ones. Okay? So their contribution would be more. The contribution of binding energy for from the nucleons inside the nucleus will be more, because they can bind with say 6 people. Now all the 6 people are available. Then they will bind. Okay. Then they have used up that binding. maximum binding is used up by that nucleon. If it can combine with 6 people, 6 are available, so much mass would be lost for this, and that amount of energy would have come for the nucleons which are inside the nucleus. But what about the nucleons which are on the periphery? They can combine with 6 because they will be either proton or neutron. Each of them can combine with 4 or 5, whatever number. I don't know the number. If a proton can combine with 5, then it will, if 5 are available, it will combine. So likewise, we have a proton here or a neutron here, it can combine with 5 or 6, but there are only 3 or 4 available. So it can only lose so much. While the nucleon inside the nucleus can combine to the maximum, the nucleons outside cannot do it. So let's imagine this. There are 15 nucleons inside, and then there are 15 nucleons outside. Okay, so the nucleons which are inside, let's say that they combine with 5 each. Okay, so 50 into 5, so 550, so 250 combinations inside. But what about the other one outside? There are only 200. 50 into 4. So the nucleons outside have only 200 connections, and the nucleons inside have 250 connections, 50 connections. So totally you have 450 connections, bindings. But what's the maximum possible? If it is 5 bindings per nucleon, the maximum possible is 500. 500. So 50 inside, totally 100 nucleons are there. So 500 connections are possible. But because of the structure, the nucleons inside will have exhausted their possibilities. But the nucleons outside cannot exhaust the possibility. So you end up with just 450. You have only 450 bindings where you could have had 500. So it actually brings down the binding energy per nucleon, right? Because now how many connections you have? 450. 450 by 100. So that gives you only 4.5. What is it? Where 5 is possible, you have only 4.5. So if you have more nucleons on the outside, on this surface, okay, then the average energy or average mass or lost you lose, the average binding energy per nucleon will come down. So the bigger the nucleus, the greater the surface area is going to be. And if the greater the surface area, then there will be more nucleons on the outside, so they will contribute less than the nucleons inside. So if more nucleons contribute less, then the average energy per nucleon will come down. Okay. So the bigger nuclei will have less binding energy per nucleon. That is the reason you see it drops. So this is kind of ideal situation, okay, the best possible situation. But after this, as the size of the nucleus becomes bigger and bigger and bigger, then the binding energy per nucleon will come down. Because as the surface area becomes bigger, you can have more nucleons on the surface, and those on the surface can bind only with the nucleons below them. Because there are no nucleons above them to combine. So that space is going to be, even though they can combine, there are no nucleons. They cannot contribute. So each of them will contribute less than it is possible for them to contribute. If there are more of them which contribute less than the maximum, then the average will come down. Okay? It's like the average marks in the class. Okay? If there are many poor students, then the average marks for the class will come down. If there are many good students, the average marks for the class will go up. Okay, so it is like this. I hope you understand this. So the inference is this. The inference. Let me summarize the whole thing now. Okay, so this is how the binding energy per nucleon graph looks like. Okay, it keeps increasing. Binding energy per nucleon keeps increasing. Of a lighter nuclei, and then it reaches a pretty much a constant value, and then it drops down. So the explanation is that the nuclear force of attraction is short ranged. Because it is short ranged, a particular nucleus can only combine with particular nucleon can only combine with the nucleons near it, not with every nucleon in the nucleus. And that is why it kind of saturates. There is a saturation region. Okay, you get that. What about this region? This region, well, here there is inadequacy. Okay, there is insufficiency. Well, these nucleons can combine with a lot more, but you don't have them. You don't have many of them. For example, hydrogen. It can combine here. If you bring deuterium, then it can combine there also. Okay, you see there are only 2 of them, then combine with 1 more, or like 2 more, 3 more, whatever. Okay, each nucleon, if you can combine with 5 and don't have so many, then as you bring more and more, then each combines with whatever is brought now. So this increases. The binding energy per nucleon increases in this region. Then you reach a saturation. Once you reach saturation, this happens. But here, what happens is that as the size becomes bigger and bigger and bigger, the nucleons on the outer surface, okay, they do not combine to the maximum possible extent. If they can combine with 5 or 6 other nucleons, only 4 or 3 are available for them to combine with. So their contribution comes down. So the contribution of the nucleons outside on the outer surface of the nucleus comes down. The average of the nucleus is coming down. Okay. So the bigger the nucleus, then the smaller the binding energy per nucleon is going to be. So this is the good. So now this gives you another interesting understanding. Well, look at this. It's a light element. If you fuse them, if you bring 1 more nucleon here, what is going to happen? Because they can combine with 4 or 5, but they got only 2 or 3. You bring 1 more, then they will combine and release energy. More mass will be lost, right? So this is what is called as fusion. When I do fusion here, fusion can occur only here, because they can combine with many, but there is a lack of nucleons. So you bring in nucleons. When you bring in nucleons, they combine with the existing nucleons, then all of them lose a certain amount of mass, then that mass is released. So fusion, this is what is called as nuclear fusion. So nuclear fusion takes place here. So fusion takes place here. Then energy will be released, because when they combine, they are going to lose mass. Fine? Okay. Fission takes place here. Why? You see, the nucleus is big, okay, then can become unstable. When it becomes unstable, then it can break down. As it breaks down, you see, now you are going to get a smaller size, 2 smaller sizes now. If there become 2 smaller sizes, you see the surface area becomes less. If the surface area becomes less, then there will be less number of nucleons on each of them. So they will combine, there will be more combinations that will happen. There will be more nucleons which are well connected with other nucleons now. So when they do that, then they release energy. A nucleon which was on the surface before initially, now because the surface is reducing, can combine with some more nucleons by releasing energy. So when a big nucleus breaks into two small nuclei, okay, you can get energy. Now whatever was available on the surface now finds some more nucleons nearby, combines. So fission, nuclear fission takes place in the case of heavy nuclei. So this also will release energy. Fusion takes place here. Here you have insufficiency, lack of nuclei. So you bring nucleon, then this combination takes place. They catch and they form a bond. As they bind, they release energy. So this is lack of nucleons. But here there is an excess of nucleons. So you make them slightly unstable. They either themselves are unstable, or you can make them unstable. When they become unstable, they break, and when they break, then they break into two nuclei, thereby reducing the surface area. So on the surface there will be now less number of nucleons. So some of the nucleons which were initially on the surface will combine with the existing, with the other nucleons now by releasing energy. I want you to understand, that's why I am repeating it. So fusion takes place here because there is a lack. You provide something. Fission takes place here because there is an excess. Now you remove that excess. Now more combinations can take place now. Okay, so energy will be released. Energy will be released here. Energy will be released here, and energy will be released here too. So fusion and fission are the two nuclear reactions. They take place at the nuclear level to give you energy. So the chemical reaction is different from nuclear reaction. The chemical reaction takes place at the electronic level. It doesn't do anything to the nucleus. This electron combines with some other electron of a different atom, then energy is released in the process. So chemical reaction takes place at the electronic level. Nuclear reaction takes place at the nuclear level. Okay, when you change the size of the nucleus, either by fusion or by fission. I want you to understand this. Think about it. It's a fascinating concept. You see how far we have come as human beings. At one point in time, we did not even know that there were something called as atoms, and then we knew atoms, and after that we were trying to figure out how the atom is going to look like. Then we found out that there would be a nucleus and electrons, and now we get deeper into the nucleus. We know there are protons and neutrons there, and they combine to form the nucleus. And as we dig deeper, just by doing experiments and then doing stuff, see, you get a curve like this, and from this curve you figure out the nature of the nuclear force there. And once you know what it is going to be, now this knowledge helps you get energy. Now you know, wow, this is what is happening. So if I do fusion, I'll get energy. If I do fission, I'll get energy. You see, this knowledge finally translates into something which is very useful in real life. And that is why you have the nuclear reactors. Okay? Hope you understand this.